Hi, welcome back to another episode in Impact Evaluation. We're going to be continuing on in this class with a discussion of evaluation methods. In particular, we're going to look at the gold standard for finding a control or comparison group to estimate the counterfactual. We're going to be talking about randomized assignment. There are other methods called randomized promotion, regression discontinuity designs, differences in differences, and how we construct our sample design that we'll be talking about in later lectures. This we can consider our toolbox. Let's begin with randomized assignment. Randomized assignment comes through a lottery or some other randomized process, such as flipping a coin, drawing names out of a hat, rolling a die. There are many ways of conducting a randomization. What the randomization does for us is it determines two statistically identical groups. We talked about that last time in the sense that the means of those two groups, the sample means of those two groups, are both unbiased estimators of the population from which those two groups were drawn. When are we going to randomize? Well, there are many practical opportunities to randomize in the real world. Lots of times we have a program or an intervention for which we have too many eligibles for the available resources. We need a rigorous method of identifying the program's intervention or effectiveness. And if we have too many people eligible for a limited number of slots in a training program, or a limited amount of cash for a cash transfer program, then how do we solve that problem? What we could do is we have to decide on a method to decide who will get it and who won't. Now remember, we have people who are eligible. We have too many eligibles for too few program benefits. So who's going to get it and who isn't going to get it? One method is for us to rank based on need. Can we take all of the eligible beneficiaries and within the eligibles decide who needs it more than who needs it less? Lots of times that's problematic. So for example, when we get to the poor, it's very hard to know what their exact incomes are. So who's more poor than someone else is a big problem. And lots of times it's too difficult and too expensive to figure that out. In these cases, what we might think about doing is giving each eligible unit the same probability of getting the program or the benefit. And there are two versions of this. One, if we have a limited amount of money, say we only have enough money to treat 100 beneficiaries, but we've got 200 beneficiaries, we could give all 200 beneficiaries a 50% chance of getting the program and flip a coin who gets it and who doesn't. Many times, though, it's not that we don't have enough money to enroll everybody in the program, but we only have enough money and enough administrative ability to roll out the program over time. So we might enroll 100 this year, 100 next year, 100 every year until we enroll everybody. In those cases, our treatment group would be the ones getting it first, and our control groups would be the ones getting it later. In this case, then, we would give each individual an equal probability of going first, second, third, etc. The advantage of this is it's ethical, it's quantitative, and transparent. It's ethical in the sense when we have limited resources that everybody gets an equal chance of getting it. This is one step back from giving it to everybody. We give everybody now an equal chance. It's quantitative in the sense that when it's randomized, when we flip a coin, it's 0-1, and it's transparent in the sense that everybody can observe whether the people who won the coin toss got the program or not, and that has advantages in terms of helping monitor the implementation of the program and keeping the administrators responsible. This produces the best counterfactual, and I'm going to show you it's relatively intuitive and easy to communicate the results. Randomized assignment. The first thing we need to do in evaluation when we're drawing the sample is identify the population. The population is the universe of individuals or firms or areas to which we would eventually like to scale the program. Now, typically, not everybody is eligible or targeted for the program. For example, contraceptive implants, men would be ineligible and women would be eligible. In this case, let's think of all the black hats and white hats in the world as people who we'd like to eventually scale the program, and the red hats, the ineligibles. Then, we don't want to do our impact evaluation on the whole population. We'd like to do it on a sample. So we take a sample of white hats and black hats, and this sample is going to be where we conduct the impact evaluation. Now, if the sample is a random sample of the population, then the sample mean will be an unbiased estimator of the population. And so whatever we learn about the sample in terms of impact of a program or a policy will be an unbiased estimate of what is likely to happen to the population if we were to scale the program up to everybody in the population. Okay. Now we take that sample, we flip a coin, and we randomly, that coin decides who goes into the treatment and the comparison group. Step 3 in this process is the random assignment of the evaluation sample to the treatment and the comparison group. In step 2, we took a random sample of the population. Step 3, random assignment. Please notice the difference between random sample and random assignment. Random sampling does not give you the same properties as random assignment. Now, the random assignment of the treatment sample, of the evaluation sample into the treatment group and the comparison group has very nice properties. Since the treatment and the control groups are both random samples of the evaluation sample too, the sample mean of the treatment group and the sample mean of the comparison groups are unbiased estimates of the mean of the sample, of the evaluation sample in 2. What that implies is that on average, there's no difference between the observed and unobserved characteristics of the treatment group and the comparison group. And in this sense, they're well balanced, or they're identical. So after we provide the treatment group with the cash, we're going to, any difference in outcomes between the treatment and the comparison group, we can ascribe as caused by the program or the policy. This also provides us another nice property. Since the treatment and the control sample means are unbiased estimates of the sample mean, and the sample mean is an unbiased estimate of the population mean, the sample means of the treatment and the comparison groups are also unbiased estimates of the population mean. This gives us 2 key concepts. First, if we randomly assign the evaluation sample to the treatment and the control group, so that the treatment group and the control group are on average balanced. There are no differences between the 2 groups, so that any difference in outcomes after the intervention can be ascribed to the intervention. We have what's called internal validity. If, in addition, the evaluation sample in 2 is a random sample of the population, then whatever we learn about the impact of the intervention in the evaluation sample, that provides us an unbiased estimate of what would happen to the population if we scaled the intervention to the population. That's called external validity. So external validity and internal validity are 2 key concepts that we need for public policy. If our evaluation has both internal and external validity, then we have the best possible evidence for making public policy decisions. Now we turn to implementing randomization. We talked a bit before about you flip a coin, you might throw a die, you might pick numbers out of a hat. Really what people end up doing is using a random number generator off of a computer computerized program. A decision, though, that we have to make in the context of implementing a randomized controlled trial with random assignment is what's the unit of randomization? We have the ability to select according to the type of program. Sometimes programs are targeted to individuals or households. Other times they're targeted to firms or facilities such as schools or health centers. Sometimes we might want to take an individual or a household program and allocate it at the street or the block they live on, possibly at the town or the community, maybe even all the way up to the district or municipality. What do we need to take into account for the unit of randomization? Well, we're going to talk about this concept later, but we need a sufficiently large number of units in order to detect the minimum impact. We're going to call that statistical power. And the larger the aggregate unit of randomization, the less statistical power, the more of those units we're going to need. The easiest is at the individual or household level. If we aggregate to the town or the community, that reduces statistical power, holding the number of individuals or households constant. We're also going to want to worry about what's called spillovers or contamination, something again we'll talk about later. The idea that the treatment might spill over or contaminate part of the control group. So let's say we have individuals or households, and we're giving them, say, toilets, and we're looking at the impact on diarrhea. Well, if you treat one household, that improves the epidemiological environment for their neighbor, and so it would be a positive spillover. A way to deal with spillover contaminations is to increase the geographic aggregation from the household to the block or the community, so that there's enough separation between treatment and control groups. And so that's a reason why we might group individuals into streets or blocks, or group them into towns and communities, and randomly assign the blocks or the towns into treatment and control units. And another big consideration are operational and survey costs. The rule of thumb is we want to choose to randomize at the unit that is the smallest unit that is viable from the standpoint of spillovers and contamination, operational and survey costs, being careful to preserve sufficient statistical power. All right, so let's take an example. Let's go back to Mr. Fulanito and assigning the cash and look at food consumption. So a typical way it might be done, in fact, this is the way the randomization was implemented in the evaluation of Mexico's conditional cash transfer program, Progresa or Oportunidades. A baseline survey was conducted at T0. The communities that were randomized into the program received cash at T0 and all the way through T1. An N-line survey was conducted before the control group came on the program, and after that N-line survey, the control groups were incorporated into the program. Now, the random assignment was done at the community level here, but we followed 24,000 households in the evaluation sample. So how can we confirm that we've got good clones? So we've decided on the unit of randomization. We have chosen how to do the randomization, a coin flip in this case. We decided that the unit should be the community level. Now we've done the baseline survey and we want to verify we have good clones. Well, in the absence of the program, the treatment and comparison groups should be statistically identical. What that means is that the averages of key characteristics between the treatment and control groups should not be statistically different at baseline before the intervention is implemented in the treatment group. So we compare their baseline characteristics at T0. Here are a set of descriptive statistics, the means for the two groups in Progresa or Oportunidades, and where we assess balance at baseline or pre-program. So here we have, in the first row, we have the mean consumption per capita for the treatment group and the control group. In the control group, the mean was 233.47. In the treatment group, it was 233.4. And the difference was 0.07 with an estimated t-statistic of minus 0.39. So we cannot reject that the means were equal at baseline. Similarly, the head of household age in years, 42.3, 41.6. Age of the head spouse, 36.8 and 36.8. The last line, the education of the household head spouse, 2.6 and 2.7. That's not statistically different. The t-statistic is minus 0.006. But we do have the household head's education in years being statistically different. Here, the control group, the mean number of years is 2.8, and the treatment group, it's 2.9. The t-statistic on that difference is 2.16. Now I'm going to and that's statistically significantly different. And I'm going to come back to this in a minute. I want to point out that we have no statistical difference in a bunch of other characteristics. Female head of household, indigenous, number of household members, whether or not the house has a bathroom, hectares of land owned by the house, and distance to the hospital. In all of these characteristics, there's no statistical difference between the mean of the control group and the mean of the treatment group. The right-hand column shows you the t-statistics, and all of those are well below critical cutoff values. If I go back to the previous slide, 4 out of 5 of these were not statistically different, and only the fourth row, the household head education in years, 2.8 for the control, 2.9 for the treatment, a difference of 0.1 years of education on average, and that's statistically different from 0 with a t-statistic of minus 2.16. Well, we have to decide whether this is evidence that we're balanced or unbalanced. First of all, if we think of sampling variation, and we think of sampling variation with an alpha level of, say, 0.05, we would expect 1 in 20 times to draw 2 samples from the same distribution, the same population, that on average were statistically different, just by accident. If we look at number of variables, sampling variation would mean the same thing. We would expect out of a sample of 20 variables, 1 or 2 of them to be statistically different just from normal sampling variation. And that seems to be what's going on here. Second, the difference between 2.8 and 2.9 is very, very small. Whereas if you were to look at the next row, the difference between the education of the spouse is only 0.1 difference between the control group and the treatment group. This is the same difference. Well, the reason it's statistically significantly different in the head's case, but not in the spouse's case, is there are very narrow distributions, much smaller standard deviation in the head's education than in the spouse's education. So giving sampling variation and this specific variable, there's really pretty strong evidence that the samples are still balanced. We're not worried about the small statistical difference in households' heads' education. Well, when we look at the data, we have this table. The first row in the table is the value of average consumption at baseline, time t equals 0. And the second row is at follow-up, the average value of consumption at time t equals 1. The first row is the treatment group, the group that was randomized to get the treatment. And the second one is the comparison group, that was randomized in the comparison group. At baseline, as we said before, the difference between the treatment group, 233.47, and the comparison group, 233.4, is 0.07 at baseline. There was no statistical difference between the treatment and control group at baseline. At follow-up, the treatment group had a mean consumption of 268.75, and the control group 239.5. The difference between those two groups were 29.25, and that's statistically different from 0 at the 0.05 level. even when we throw in a bunch of socioeconomic controls, in fact, into a linear regression, the multilinear regression is almost identical to the results for the linear regression. So we, using random assignment, estimate that the impact of giving the treatment group cash was to increase their per capita consumption by 29.25 per capita. We might think about a different type of evaluation question. Our traditional evaluation question is, what's the impact of a program on a result? Other relevant questions have to do with how best to optimize the program. If we changed the benefit design, would we improve outcomes? For example, what's the optimal level of a benefit? What's the right level of the cash transfer? We also might think about asking whether complex programs that have many subcomponents, whether each of them independently adds value, or whether all the components together are superadditive. In this case, we have to unpack the impact of the program into each of its components and the sum of its components. So an example might be to think about changing the amount of the cash transfer. We might think about a low benefit and a high benefit. Which one yields higher results? If we provide half the cash or twice the cash, the low benefit and the high benefit. If we go from low cash to high cash, do we get more than double the benefit? In that case, the high benefit would be more cost effective than the low benefit. If we go from the low benefit to the high benefit, but we get less than double the benefit, then the high benefit would be less cost effective than the low benefit. Well, we can implement a high benefit and low benefit design by creating 3 arms of the study. As usual, we conduct a random sample to create our evaluation sample, and now we randomly assign those into 3 groups. A pure control group or comparison group that receives no benefit, a second group that receives the half benefit, and the third group that receives the double benefit. So here we have 3 arms of the trial: a control group, treatment 1 half benefit, treatment 2 double benefit. So now we might ask the question is, how do 2 benefits complement each other? In this case, we can compare one subcomponent to the other subcomponent to the combined groups. So here we might think about having 2 treatments. One treatment, one intervention is cash. So the rows would be cash. The first row is the comparison group, where they get no cash, and the second row is the treatment, where they get cash. Intervention 2 is picked up by the columns. Here we provide transport. Column 1 is the comparison group. It has no transport, and column 2 has transport. That would be the treatment group. Well, with this type of design, we have 4 groups. The first row, first column is the pure comparison group. The second row, second column is full treatment. You get both cash and transport. Group C is just transport, and Group B is just cash. So then this allows us to make a number of comparisons. By comparing Group A to Group C, we get the effect of transport by itself. By comparing Group A to Group B, we get the impact of just cash. By comparing Group A to Group D, we get the impact of both. By comparing Group C to Group D, we get the impact of cash on top of transport. And by comparing Group B to Group D, we get the additive value of transport to cash. Well, in order to implement this, we send our random assignment to a 4th group. We first draw our evaluation sample by random sampling in order to have external validity. We then flip a coin where we allocate the evaluation sample into the treatment and comparison groups for intervention 1, and then we flip a coin again to allocate each of the groups that were assigned to the first treatment into treatment and comparison groups for the second treatment. So remember, random assignment of a benefit to a large population produces two statistically equivalent groups, two groups that whose sample means are unbiased estimates of the population mean. In this case, we have what we call the perfect clone. We have balanced treatment and comparison groups. It's feasible in prospective evaluations whenever demand exceeds the benefit, exceeds the amount of resources we have for people, or we have to phase them in over time. Many pilot programs meet this condition, and so there are many opportunities to do random assignment in the real world.